Welcome all to the sixth presentation in this fifth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. We'll continue to have these monthly webinars throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the remainder of this fifth series will be distributed through the IAS mailing list and via the IAS Twitter account. Today's webinar will be given by Dr. Matteo Gazzani at the Copernicus Institute of Sustainable Development at Utrecht University in the Netherlands. I am David Donacci from Imperial College London in the UK, and today's webinar will be moderated by Giuseppe Pezzella at the King Abdullah University of Science and Technology in Saudi Arabia. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask you to consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to the IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter @intadsoc for future updates regarding IAS events, webinars, and information about scientific meetings. And please help expand our YouTube channel by liking this video and subscribing. I will now hand over to Giuseppe, who will introduce our speaker for today and who will be moderating the YouTube Q&A.
It's my pleasure to welcome Dr. Matteo Gazzani to today's webinar session. Dr. Matteo Gazzani is Associate Professor at the Copernicus Institute of Sustainable Development, Utrecht University, and part-time at the Chemical Engineering and Chemistry Department of TU Eindhoven. He receives his bachelor and master's degree in energy engineering from Politecnico di Milano. He obtained his PhD cum laude in energy and nuclear science and technology from the same university. Prior to joining Utrecht University, he was a postdoctoral fellow at ETH Zurich. His overreaching goal is to facilitate the transition to a climate-neutral society, and his research focuses on improving the design and the understanding of new chemical and energy processes, like in gas separation, by bridging fundamental science to the process and system level. Recently, he has worked on TSA, PSA, and VPSA processes for hydrogen and CO2 separation, including from air. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Matteo Gazzani again and pass over the presentation to them. Thank you.
Thank you. Let me share my screen. All right. So thank you very much, Giuseppe, for the kind introduction, and David as well. And most of all, IAS for inviting me to giving this webinar, which I'm happy to do so. So yeah, so I'm going to talk about assessing and optimizing adsorption processes from a plant and system perspective. But before doing that, I wanted to give some more personal background. So I'll be looking at time, elevation, and adsorption lines. I was born in 1984 in a beautiful place Here you see some pictures, north of Italy, where the elevation is about 1,000 meters on average, I would say. Then I moved to Milan for my studies, as already mentioned by Giuseppe. And then during my PhD that I did still in Politecnico, I also started developing my knowledge in adsorption, working on adsorption enhanced water gas shift, so a sort of reactive VPSA, and also on membranes for hydrogen separation. Then I moved to Zurich as a postdoc, decreasing the altitude to around 400 meters, but increasing a lot my, let's say, knowledge in adsorption. I worked there on TSA, VPSA, PSA with Marco, Lisa, IAS, and many others, and for looking at separation of CO2, hydrogen, and nitrogen as well. Then I continue the line with reaching about zero level, so close, if not below. And today I'm a associate professor in Utrecht and in TUI, and I still work on adsorption quite a lot, mostly looking at challenging separation like CO2 capture from air and methane also removal from very diluted streams. All right, having said that, I would like to start with why do we need plant and system level analysis? And I like to walk you through an example. So here you see two technologies. One on the left, you might be familiar with that, is carbon capture from a power plant in Texas, a Petronova plant. And on the right, you see a fuel cell for automotive, for transportation in personal cars. Well, you may wonder, what do these technologies have in common? I would say that deployment at mass scale in the expected time failed for both. That's interesting to see that there were a number of common reasons. So there was a wrong primary market on power. CCS look at power sector as the very first application. The fuel cells work to personal transportation. And in both cases, we have big limits from an infrastructure perspective. So CO2 storage and transportation for CCS, and hydrogen production and refueling stations for hydrogen. And also, in both cases, we had viable alternative solution, PV and wind turbines for power plants, and the battery electric vehicles for personal transportation. Also, in both cases, there were a lack of, let's say, big enough market. Markets were very localized. Instead, the big national or international markets were missing. So lack of CO2 emission market, lack of a hydrogen and fuel cell vehicle market. And finally, last but not least, they both experienced problems when it came to the societal acceptability. So notably CO2 storage or hydrogen on board, let alone the cost of fuel cells vehicles. So this just to say that essentially technologies really need to be developed while keeping in mind their role in the broader energy and material transition. Otherwise, the risk is that we develop technological solutions that are beautiful and work very well, like the two that we see now in the back there, but they miss their role, and they will miss the deployment at this required scale that we need for the energy and material transition. Now, if we focus a bit more on the CO2 capture one, it's interesting to see here that starting from around 2010, the number of studies on adsorption-based CO2 capture has really picked up. Today, we have around 400 and 500 papers published every year on the topic of adsorption-based CO2 capture. Well, at the same time, I borrowed a picture from a play, Waiting for Godot by Samuel Beckett, where two actors are basically discussing when does Godot come, but he never arrives. And some sort also CCS and adsorption-based CCS. It's still, where is it? So it's not there yet in terms of, again, deployment in commercial plants. In fact, if we look at the cost of CO2 capture, we can see that in the early, when the technology was started to take off in the let's say in academia, there were predictions on the cost by IPCC that were in the order of 50 to 100 plus euro per ton. And there was also at the same time a target set by the DOE around 25 or $70 per ton of CO2. Now, 20 years has passed and more, and we have built a few plants, more than this when we consider also not power application, but if you stick to the power application, Boundary Dam, Petronova, and maybe Shend, and the cost has not decreased. Of course, what would you expect from a real plants, first of a kind plants? But notably, if we also now plug in also a lot of numbers from research, so the research has been developing and producing a lot of material from pilot to laboratories to simulations, we still see that the cost actually went rather up than down. So again, creating a sort of disconnection between the expectations, especially the DOE targets, and what was then identified by the many researchers. So creating again, essentially giving a sort of reason not to deploy the technology because it's perceived as expensive, when it's not really expensive if you think of the role of CO2 capture in the energy transition and in the mitigation of CO2. This was a kind of an introduction to say that essentially we always need to reach the level of plant and system levels. I really encourage researchers to develop adsorption technologies, also looking at the plant and system level. At the same time, I think that there are cases where it's more relevant than others. So for example, when adsorption is really a key enabler of the separation, so like the separation of highly valuable molecules, fine chemicals, for example, mainly done by chromatography, the separation of toxic compound like volatile organic compounds, whenever you have a very strict environmental regulations, also for application like wastewater and soil remediation. So in these cases, plant and process level is important. It is important for the optimal plant performance, but is not really vital because the adsorption technologies in this case are really those that make the separation possible. So you want to get a better plant, essentially, better economics, but if you don't do that, if you don't do the technology development following the plant and the system level, it will not prevent the use. However, there are other cases where this is not true. So when adsorption is an option among several solutions, if we want to separate molecules in a very large amount, like in CO2 separation from flue gas or hydrogen separation from syngas, or even air separation or purification of biogas, where we have a number of alternative solutions, it's really important, actually I would say vital, as I wrote, that the technology development is done along with the plant and the system level, or actually rephrasing that the plant and system level steer the technology development in the right direction. This is also true when the separation relies on strong interaction with the outside world, so the system, the electricity system, the heat, when we have a large heat demand, like for direct air capture, we really need to couple the technology to the energy provision and the system. All right, so this was a kind of a short introduction, and then I would like to clearly say what is the goal of this presentation. It is provide a first understanding of the key modeling pillars to assess adsorption processes merging column to system levels. And I've prepared these slides thinking of graduate students, early career researchers, practitioners that are new to the field of adsorption. All right, in terms of the rest of the presentation, we are going to focus on the building blocks for plant and system level analysis, going from the reactor or the column through the process, the plant and the system level. And we will do that by also looking at examples of applications. Now, first, a few remarks. So when we want to basically merge the reactor to the system level, these different levels need to be able to talk to each other. So reactor models need to be embedded in the system level, and the system level should provide insights that are relevant also for the column and reactor modeling. Therefore, it exists a trade-off between the complexity, the accuracy, and the capability of establishing an integrated assessment framework. And overall, I would say that we need to adopt methods that allow to retain physical behavior, but they have to be simple enough to avoid entering computational or arriving into really serious computational hurdles that can't be overcome. So we need to have the right level of simplicity while retaining the physics of the system. All right, let us start from the adsorption column. Well, here we have a really simplified description of the physical system. So we have a column or whatever contactor where we know there will be a solid phase, an adsorbent, and a void phase. And this system is described by a number of properties, thermodynamic properties that are relevant. So when we want to simulate this such system, we have very powerful equations to do that are partial differential algebraic equations that describe the mass balances, the energy balances, and the momentum balance, for example, with the Ergun equation along the bed. These, of course, need to be then coupled with relevant initial and boundary conditions like the feed condition, the pressure, and what we fix at the boundaries, like the inlet again, the outlet, the wall, for example. And there will be a significant number of model parameters that we need to take into account, like the physical properties, adsorption equilibrium, extremely important, of course, and with the isotherms, and also mass and heat transfer coefficients or models. When we would want to translate this into models, we have essentially three different relevant approaches. One is a very simplified 0D, well-mixed reactors. Then we can discretize this in one direction, the 1D, and then I put together the 2D or the 3D as the more complex version of the resolution of this system. Now, the 0D, yes, it's a very fast. It has the nice feature that can predict trends, but is also, of course, inaccurate. No, the adsorption relies on fronts, and we are here getting rid of fronts and mixing everything mathematically. So they will be inaccurate to a certain extent. So these are good models for when we want to design the process, or we want to conceptualize the process, and when we have to do large screenings, like a material screening, for example. 1D models are instead reasonably fast. They have really a good potential to match with experiments, especially if we treat carefully the different mass and heat transfer coefficients. And they can be used, because they are quite accurate, they can be used for process models. Last but not least, we have the more complex 2D and 3D models that are, of course, slower because of the number of discretization points they have and the complexity of the resulting equations. We have that has also the potential to match very well with experiments, and they are very accurate. But the purpose of this should be to really design the system, to get a much more detailed understanding of the flow within the column, and therefore do that step before, for example, building a system. So when we look at this in terms of we want to bring this level to the system, I would argue that the 1D models are the preferred solutions. They are reasonably fast. They can be embedded. So my suggestion would be really start your analysis with 1D models. 0D can also work, and again, especially if you have certain applications in mind where you have a lot of point evaluation or very expensive optimization or time-dependent optimization. While I would say the 2D and 3D models are that are based on thermodynamics. So these are, I would suggest not to start there, because it's not. I think it will be difficult that it will work out. Please use experiments to validate the model. So there are really a lot of experiments, a lot of literature on breakthrough curves, and also based on small pilots that you can find in literature. So always you start with a 1D model, and when you are confident enough that your 1D model behaves like your intuition, like your physical intuition describes, go to the validation with experiments. And you don't need a setup in-house. You can really take data from the many papers that have done this. All right, now after the column, we need to go to the cycle, to the process, essentially. Let's call it the process. So we need to model now the process for the adsorption process. And it happens that most of adsorption processes are carried out in fixed bed, like PSA, TSA, VSA, VPSA cycles. These are transient in nature. They operate at cyclic steady state and instead of a true steady state. For example, here I'm showing a TSA cycle. So this is for a CO2 and nitrogen separation. So we have the column undergoes this different sequence in time. It will CO2 will adsorb first. Then we need to take care of producing CO2 at high purity, the purity that we want to reach. So we have two steps that enable that. First, pushing the nitrogen out with a rich CO2, and then enriching the bed with CO2 after we have recovered the CO2 product. And then we need to cool it down to go back to the starting point. Another type of cycle is, for example, a VPSA, vacuum pressure swing adsorption, for the separation of CO2, nitrogen, and hydrogen. So this ternary mixture, where we have even a more complex cycle, where we have a number of adsorption, pressure equalizations, rinse, purge, that eventually allow to separate this ternary mixture into the CO2 product, the hydrogen product, and a waste containing nitrogen and a bit of CO2 and hydrogen. So I'm showing these cycles to say that cycle design is a critical step, that even when you do plant and system level analysis, you can't underestimate this, and you really need to take this into consideration and do the proper cycle design that you would do whenever designing a process, even if you intend to evaluate that from a plant and system level. That's because really the cycle affects the performance tremendously, and it's a building block of evaluating adsorption processes. Interestingly, this is of course true for a fixed bed and experiencing a cycle in time, but is also true for a case where you are for a different configurations where you do have a steady state, like with a fluidized bed. This is an example of a fluidized bed with adsorption and regeneration. So it's a different type of process, still relying on adsorption, but on moving the solids rather than using the different distribution in the bed of the gas and the solid. And let's say that the equivalent cycle can be designed now in a way in space. So you can identify the right cycle in space by subdividing the different the two main reactors into a number of reactors. So even when you have a continuous process based on adsorption, please take the reactor configuration, the process configuration into account whenever also you want to do the plant and the system level study. Now, a few key points that I would like to highlight here. So first of all, that identifying cyclic steady state conditions is computationally extensive, because you need to solve the column level that we have seen before in an iterative way. For every step, you need to solve the equation, and for every different type of step in the cycle as well, you need to solve this, and you need to do that till you find out that the internal composition, the temperature profile do not change, the product composition does not change, and the total mass balance is indeed respected. So the typical approach, the common practice, is to use a fixed point iteration. So this means that you from a one simulation, you take what you find as a status, and you send it back as initial conditions for the next iteration. most of the simulation tools actually use this approach. It's very solid because you go really, as it says, step by step, but it's also quite slow because you will need a large number of evaluation to identify the cyclicity state. So I would argue that the state of the art with this respect is these are tools that develop that use different so that speed up, accelerate the iteration, like with using Newton type or perturbation methods. Levan has done a lot on this, but the problem with this method is that they really require in most cases they require, for example, the computation of the Jacobian. So you gain in the acceleration of the cyclicity state, but you lose in the time to compute what you need for that acceleration. So new solutions try to go beyond that, and I would say that there are two interesting solutions to this. One is vector acceleration methods. And recently, Gokul Subraveti in SINTEF with us, we have done some work on this, and we have implemented for two different cycles. This one that you see is a VSA for the CO2 and nitrogen separation. We have implemented two possible acceleration methods based on vector acceleration. One is Irons and Tuck, and the other is Graves and Morris, and that essentially allow to accelerate the cyclicity state without the need of computing derivatives, the Jacobians. And you see this with these two terms here. And I'm reporting here some results. You will find more in this open access paper if you Google it. You see that the fixed point iteration goes to cyclicity state in around 300 cycles. And when we implement these vector acceleration methods, you basically go to 200 with the Irons and Tuck, and even 230 with the Graves and Morris. So the acceleration is really relevant. Think that essentially every cycle may take up to a minute or 30 seconds. So the number of cycles, the amount of time, the computing time that you save with this acceleration is remarkable. And also the nice feature is that as I showed in the slide before, with the fixed point iteration, you need to bring the solution back to the evaluation as an initial state. So this is not different with this method. The only difference is that the guess that you are using is a bit smarter than the fixed point iteration method. Another interesting approach is the data-driven method. Sorry, I wanted to also show this for the TSA. So we did also the experiments on the TSA. So here you see a slightly more complex TSA compared to what I showed before, but is again for CO2 and nitrogen separation with adsorption, purification, 2 steps heating, and recooling. And again, consistently with what I've shown before for a VSA, we have a significant reduction in the number of cycles required to the CSS. And in this case, TSA, they converge with a lower number of cycles, but every cycle, because of the length of the cooling and heating step, the total amount of time will still be very relevant. So in terms of computing time, this saving of cycles is equivalent to the savings that I showed before for the VSA. Yes, and then the next approach that I want to discuss was the data-driven methods, and this has largely been done by Pai and in the group of Arvind Rajendran, and they have done a lot of work on this. And they have shown that this idea works very well, very nicely. So what you can do, you can use an artificial neural networks to predict the cyclicity state conditions, and these cyclicity state conditions are used again as an initial solution for detailed 1D models. So the idea is always the same, a bit in a way. So try to find a smarter way to predict your initial condition for the 1D model. And you can use data-driven methods, and you see here the saving again, it's very remarkable. So you go to a mass balance error that is within the limits with 6 cycles instead of 60. Yes, 24, sorry. Or you can do it with the vector acceleration method, but eventually you have a faster approach to cyclicity state. If we continue looking at the needs for process modeling, I would say that something that is often underestimated is the scheduling of the cycle. So the scheduling is really needed to take into account all the idle times that will be present, especially for complex cycles. Whenever you have pressure equalization, whenever you have coordinated rinse and purification steps. For examples, this scheduling will allow you to consider continuous feed. That's something that you in a continuous process you want to have in a continuous plant. So let's think of a refinery. You want to have a continuous production of hydrogen in a way. You will be able to synchronize pressure equalization and also to produce continuously your product. So when you include this scheduling, the performance of the cycle will change. I'm reporting here some results for a hydrogen CO2 nitrogen PSA, and you can see that the productivity that is on the x-axis of the cycle without scheduling is significantly larger than the productivity with when you include scheduling. So we go from 550 kilograms of CO2 per in time to down to 350, and that because if you want to have a complex cycle that deliver in separation, you need to have enough number of columns. Then I will also say that adsorption processes are complex and not necessarily intuitive. There are a lot of variables and the interplay between the different properties. So I think that we really need to make use of this nice tool that is rigorous mathematical optimization to identify the optimal conditions of the technology. Of course, working with a sensitivity approach, so like scanning different values and see with your hands in a way what how the system reacts is always useful to gain to improve the knowledge of the user. But eventually, I think that the process design should stop when a mathematical optimization is carried out. And I would like to discuss more in detail this part. So there are a lot of decision variables that are possible. So I'm listing here some, for example, the adsorbent material decision, the reactor geometry, the cycle configuration, the cycle step timing, which is very unintuitive at times, the column length, temperature, and pressures. So these basically lead to three different three main classes. So one is really the cycle, the operation of the cycle in terms of time step, temperature, and pressure. One is about the materials, what materials do I choose, and the other one is really the cycle configuration. So how do I arrange the different columns, what steps I need. I would say that while, let's say, cycle configuration materials are important, but are something that are difficult to bridge to the plant and process level, at the time step, the temperature and pressure, mathematical optimization can be embedded in the plant and in the system level optimization. Now, if you look at the possible approaches for this optimization, we have three main possibilities. The first one that you see here is a black box approach. So what we have is we have a bed model, that's let's say the cycle model, and the cycle will need to compute the cyclic steady state that we have just discussed. And on top of this, we can have the optimization. We can optimize for a number of objective functions. We go back to this later. But essentially is a hierarchical approach: the model, the cyclic steady state, and the optimization. In a second approach, we can bring together the optimization and the CS and the cyclic steady state. This has been done by Pantelides and co-authors, for example, and you can ask your algorithm, your optimization algorithm, to fulfill the cyclic steady state condition as part of the constraints of the optimization problem. And let's say the most extreme case compared to the hierarchical one on the left is where I want to solve everything in once. So the equation-oriented approach, where we bring in optimization, the bed model, and also the CSS, and also the partial differential equations together in one, and we solve everything in one go. Let's say that the 2 and 3 are of interest, but I think that for adsorption processes, the first approach is the state of the art, and also the one that allows to interplay with materials and with contactor design easily. There are advantages and challenges in this approach. So we have a lower number of, if you look at the advantages, we have a lower number of variables. We have a feasible path typically, because we solve this hierarchically. It's, let's say, well-proven. We have well-proven solvers that can take all the PDEs in the model. It's robust. And it also mimics, in a way, the dynamic of the reactor, because the cyclic steady state does nothing that mimicking what a reactor would do when being operated. So we have insights on the dynamics as well. There are challenges that the challenges are indeed also in the dynamic and the cyclic behavior. So it's a difficult, mathematically difficult problem to solve. We have a tight relation between reactor design, cycle time steps, and scheduling, and numerical solvers may not converge. So we may have basically non-continuous objective function. And the bed model and the cyclic steady state, as we have already mentioned, they are in computationally intensive function that may take from a few seconds up to minutes. What are the computational approaches to this? So I think that there are three main avenues to this. So we can solve this optimization problem acting on the bed model. And this means that we, instead of using a detailed model, we use surrogate models of the 1D. We will go through this later. The second one is act on the CSS, as we discussed before. So really try to do the optimization with an improved CSS computation, so that the overall the objective function evaluation that the optimization sees is not particularly computationally intense, because we do it in a smart way, the CSS. And finally, we can act on the optimization algorithm itself. So we can think of tuning algorithms or designing algorithms that deal with the problem, with the features of adsorption with cyclic steady state type of features. Now, let's start looking a bit more at the first. So I'm taking this from a recent work of Anne Streb and Mazzotti. So what they did was they had a 1D model, and they, based on that, they trained an artificial neural network with process parameters and feed computation, and they made a surrogate model by training an artificial neural network using data from the 1D model. So this is, in a way, it's a rather a simple approach, especially with the many tools that allow to do this, allow to do that today, like just the MATLAB or the Python package for this. And then what you can do is use, for the optimization, use the artificial neural network. And interestingly, you can think of use a combination of the 1D model and the artificial neural network. They have shown that, in fact, that works rather well. So here you see the energy consumption and the productivity of a VPSA. So again, the hydrogen CO2 and nitrogen separation cycle. And you see in dots, in diamonds, the full model, and in terms of the Pareto fronts that are found by the optimization for a purity of hydrogen larger than 99.9% and larger than 99. And you can see that essentially the surrogate model, that is the continuous line, found the very same Pareto front of the full model. So this is, I think, it's a very promising approach. Please be careful with your training. At the end, everything here boils down to do the right training and use the right approach there. when we look at the second approach, here I'm using the work of the group of Arvi and Rajendran that have recently worked on this, and they compared the approaches of detailed optimization, so that connecting the genetic algorithm to the full model, the surrogate approach, again, using artificial neural network and also a number of other machine learning approaches, and the case with speeding up CSS via, in this case, with data approach. And they have also shown that this approach of speeding up the CSS works rather well. So here you see the detailed model in black, the continuous line in black, and the surrogate model, so this one, with the red dash line, and the case where CSS was accelerated via the neural network in blue. And essentially, the nice take-home message that for both separation performances, so recovery and purity, and energy and productivity, the black line and the blue line substantially overlap. So these are, again, very promising approaches to enable optimization while getting over the problem of the computationally intense algorithms. The last one is identifying the right optimization routine. So that's where we have worked a bit more. And I would say that there are a lot of opportunities in this in this field as well. So essentially, there are different optimization routine that you can use. So you can use gradient-based, evolutionary population-based, or model-based, derivative-free. Of course, when you have a function that might not have any value, so discontinuous, the gradient base become very challenging. The evolutionary population-based models also have problems in terms of did it identify the global and was the convergence guaranteed? And typically, they really need a lot of evaluations, so a lot of objective function evaluation. Model-based derivative-free open opportunities for this, and they, with the fact that they are derivative-free, they allow for global search, they have a guaranteed convergence, and they use a model to save evaluation. Of course, here in this case, because we need a multi-objective approach, and I will come back to that, we will need a sequence of single objective optimization, which will be quite challenging. So what, for example, I mean, I would say that there are multiple solutions. We started a few years ago with looking into this multi-level coordinate search algorithm, but interesting work has also been done looking at coupling Bayesian optimization and the genetic algorithm with what is called the CEMO algorithm. And I'm just focusing on this here, but I encourage you to look into also alternatives. So the multi-level coordinate search is an algorithm that allows to screen, to map the design space very well by if you look here at a case where we just have two simplified version with two variables, it splits up the space in different regions, and it allows to have local searches with surrogate models around the most promising regions. So by coupling this global approach with the local search, it is in effect quite fast. The problem is that this multi-level coordinate search is for a single objective. So one needs to, that's what we did, one needs to think of a solution to make it multi-objective. And one can do this using a weighting factor, but that will probably might lead to problems with respect to non-convex Paretos. And a better solution is to use a normalized normal constraint where we can identify Paretos by fixing a normal line and by exploring all the points that are above the normal line. And this allowed to have a very well equidistributed Pareto front, and also to identify cases where the Pareto is non-convex, so it has like a strange S behavior, for example. Here you see some results that we showed a couple of years ago, where we basically were able to identify the Pareto front in blue with this multi-objective MCS with a CPU time of 50 minutes, while let's say the easy to implement cases like MOPSO, DMS, SA, and the genetic algorithm required around 6 hours. Again, this goes in similar to the approaches of 1 and 2, goes in the direction of enabling us a faster optimization and a faster screening of the promising objective function, so as to identify really what is optimal. Now, I think it is worth spending a few words on what do we need to optimize. There are multiple objective functions that are of interest in adsorption-based separations, and I think that one should always start with the separation performance. So minimize, here I'm having an example of CO2, so minimize or actually maximize the productivity and maximize the recovery and the purity by changing the different operating variables. This will allow you to identify the right conditions and the right design space for the variables, but also the right cycle. So you see here that we had a simple cycle. This simple cycle does not deliver the recovery and purity that we were targeting, 90% recovery, 96% purity. While an advanced cycle here with the dashed line enter that space. So this is a two, let's say that the separation performance allow you basically to kick out whatever doesn't deliver in terms of the minimum standard that is the separation that you want to have. As a second step, then you should look into energy and productivity. You can bring in constraints in terms of separation performance, and you can limit the operating space from the step one. And this typically will lead to Paretos in terms of energy consumption and productivity that you see here, for example, for a TSA, we had this Pareto, and you can also then put that into in perspective of what other processes like absorption processes could deliver. The last step, and this is especially needed if you really are designing a commercial separation, is the economics. So you can use capex and opex as or the sum of capex and opex with a capital recovery factor to optimize the economics of the cycle. And by doing this, you may find interesting things, like for example, that you see here from again from the work of Supraveti and Arvind Rajendran, they identified that the minimum cost cases, these black and this blue and red are for different materials. The minimum cost differs from the maximum productivity or the minimum energy. So in a way, these three steps that I was showing before are really helpful to go to the optimal case, and are really needed to identify how your system behaves depending on the different boundary conditions. All right, let's move now to the plant. The plant will be quite quick. So when we go from the process to the plant, I would say that we have two main cases. So in one that you see here on the left is a simple plant. This simple plant, for example, might be the adsorption process plus the impurities, or the adsorption process plus heat integration. In a second case, instead you have a much more complex plant. For example, when you want to have the full industrial process, think of again of a refinery, or the example I will give you later, or TSA in a cryogenic air separation plant. Now, if you look at the simple plant on the left, the example here that I'm showing is a removal of water along with the TSA that we discussed before. For example, because your material like a zeolite doesn't really want you don't really want to have water in the feed. So the suggested approach here will be keep the adsorption model with the 1D, the same adsorption model that you have used with optimization. So this plant level analysis can fully rely on the 1D model or any surrogate model that you have proven working well. Then you can add simplified energy mass balance for the additional components. These can be heat exchangers or, as I said, the drying unit beforehand. When you go to complex plant, and here I'm showing an example of from my PhD studies of we wanted to integrate the adsorption enhanced water gas shift in an integrated steelworks. We had a lot of different reactors. We had a lot of different power equipment like gas turbines, heat exchange, heat recovery, steam generators. In that case, it will be very challenging to use the 1D model. So my suggestion would go for a simpler model. But be sure to stick to the physical behavior. So this is nicely done by a 0D model or a trained neural network that still you have proven to behave correctly in the whole range of operating conditions. And then you can add the energy mass balance for all other equipment. For example, in this case, we were simulating in quite detail with the 1D model the gas turbine because we were particularly interested in that as well. So you need to find the right equilibrium between the description, the thermodynamic description of the model, and here again, simplifying the adsorption process at times is an option. Now, moving to the system level, but first I think we need to describe what is a system. So a system is the union of a process and plant together with everything that counts from the outside world. So typically we have our adsorption process embedded into a plant where we have a number of processes, and this plant needs to interact with the system. So for example, it interacts with electricity price, with the electricity market because we consume a lot of electricity. We interact with electricity, with the CO2 emission market, but we can also very physically interact with the weather conditions. Think of, for example, of direct air capture, or we simply want to interface with the market, with the product market. Think, for example, of a hydrogen market where we are not bounded to a specific site, so like in a refinery, but more open hydrogen market. In these cases, we really need to integrate the adsorption process and plant with the system. However, the problem here that you will have is that typically these different variables have a large fluctuation in time, and they call therefore for a substantially different approach. I'm taking the example for the remaining of the presentation presentation with direct air capture. So a work that we have done. This was also presented at the last FOA conference, and because I think it represents the system level requirements quite well. Here you see the Climeworks plant in Iceland operating in a summer spring time versus a autumn winter case. So indeed, the type of the temperature and humidity of the air entering the contactor is completely different. Here you see some examples of temperature and humidity profile. This is for California, however, but you see, I mean, the key point is that they have large fluctuation every day, every hour, but also seasonally. So you need really to take into account for the fluctuations that happen at hourly level, but also the fluctuation that happen at yearly level. The point is that your material will behave very differently depending on this ambient condition. So if it is, for example, when we use an amine based sorbent, we will have a certain behavior with respect to water. So the relative humidity, we might have an enhancement factor because of presence of water. But also when we go from a low temperature to a higher temperature, adsorption being exothermic will suffer of higher temperature, and therefore the capacity of the sorbent will decrease because of the temperature that is increasing during the day or during the month. So the question is, what type of modeling framework should we use in this case? Well, the approach that we showed before, where we have time and space discretization with the 1D model, it's difficult to handle when we want to have an yearly evaluation. These models, the 1D model that we have seen, they have a resolution of seconds, because that's what we need to even below seconds, because that's what we need to reproduce to mimic the system. And when we go to cycles, this might take minutes to maybe a couple of hours, say for long TSAs. But the point is that we can't use these models for an year level, so it's not really an option, and we need to find a different approach. So what we suggested in this case was to bridge thermodynamic modeling with a mixed integral linear modeling, because mixed integral linear modeling is a very nice approach to screen long time horizons, while the thermodynamic modeling allow to predict at a lower resolution, time resolution, the performance. So what we did was try to find a bridge between the thermodynamic model, that is basically what I've shown you before for the classical approach to adsorption technologies, with a mixed integral linear programming that can handle the long time horizons, year, but also multi-year, in fact. So in this case, the first step that you need to do is prepare the thermodynamic model for this application. So you will need to screen. You will need to screen different temperatures, different humidities, whatever different factors that varies in time. For example, it could also be for different electricity prices, and you have a TSA that is driven by electricity. You may want to see what happens if I modulate the power that goes into the TSA. In this case, it was different, and it was the weather conditions. And then you can get the Pareto fronts for productivity and specific energy, and you can bring this into an input-output relation for the mixed integral linear model. In the mixed integral linear model, we must use linear function, but you can also use function that predicts well in fact the thermodynamic behavior. And we can use then, along with the linear function, we can use a number of constraints that allow us to retain this physical behavior. For example, limit the number of changes in cycle parameters in time, boundaries for energy input, the number of operating modules that has to be smaller than the total number of modules, and we can also look at different type of energy input. For example, this function for direct air capture, we rewrote that as a piecewise linearization. So depending these different linear functions that are piecewise built, that where we had the CO2 output of the direct air capture technology function of the energy that was provided to the direct air capture system and the number of operating parameters. And these alpha and beta these will be coefficients that are obtained from these graphs, where we have also dependency with these theta parameters on the weather conditions. Eventually, you will transform this Pareto function into an input-output relation, where we have the CO2 output, for example, in terms of as a function of the energy, as a function of the temperature, and as a function of the number of modules. And you can do that by then screening the whole possible weather conditions in terms of, for example, relative humidity and ambient temperature, and interpolating adequately between the different points, resulting in these maps. And these maps then are de facto your input for the mixed integral linear programming. Eventually, this type of bridge, this type of overall framework, where you bridge the typical thermodynamic approach to adsorption with the typical time discretized, long time discretized mixed integral linear programming, this will allow to identify interesting behavior, for example, with as I said before, a changing boundary condition like the weather, the price of electricity, so on and so forth. And here I'm showing an example that where we had this yearly time evolution of temperature in blue and humidity in orange, and we were able to identify different operating conditions of the system depending, for example, on how you control how you want to control the cycle itself. Right, I'm taking a bit of time, but I'm finally at the conclusions. So I would like to wrap up a few take-home messages. So I think that the evolution of adsorption-based technology should always extend to the plant and system level to ensure that the right role of the technology in the system is investigated, but also to address the relevant technological challenges. It might happen that you don't really need to focus on the material for a certain, for example, TSA, but you should rather focus on the contactor, or the interplay of the contactor and the material, or the dynamic changes of the contactor material in time if you have a fluctuating flue gas flow entering. So again, this system and plant level is important to really understand what are the key challenges that need to be addressed. It is possible to have an assessment that bridges the process and system level over different length and time scales. However, you really need to pay attention to choose the right combinations of models to have at the end something that is computationally treatable, so computationally reasonable framework. When investigating adsorption technologies at plant and system level, the physical behavior must be retained. So this is, of course, very important. So try to really, as much as possible, maintain the physical description at the higher level. Mathematical optimization has a key role in the improvement of adsorption technologies, but you need to be, again, careful in choosing the right optimization algorithm for your application, and just don't necessarily go for for one or the other option. Really try to ponder what would work best for your case. Several opportunities exist for machine learning in general, which I think it's great, but they are not always required. So I invite you to really think, is machine learning what I need to do to proceed? Sometimes sticking to thermodynamics is better, and so I really weight well what are the needs of your process. Finally, bridging methods and disciplines really opens new opportunities. So you can recognize similarities, but also while also keeping in mind differences, this allows to see things from a bit of a different perspective. And with that, I've finished, and I'm happy to answer questions that hopefully we have.
Thank you so much, Professor Gazzani. It was an amazing presentation, and I was literally shocked by the results that you have presented so far. In the meantime, I'll go through the YouTube question. I'd like to ask myself some questions, if you don't mind.
Of course, yes.
Slide 36.
All right, maybe I'll do.
Yeah.
Slide 36.
Yeah, we were talking about the Newton approach, the vector acceleration methods, and so on. But I have a question. For example, in which case, I understand that they might complicate the algorithm of the modeling and then the computational time of the modeling itself. Is that correct?
Well, when you do the typical Newton approach and similar, where you need to compute the derivatives and the Jacobian, that will complicate significantly, because the computation of the Jacobian for real application is not something straightforward. These type of approaches, instead, they don't really complicate particularly, because these operations are very straightforward, and you are basically operating, you are just doing some operation on the different set of initial conditions. So you are connecting, for example, here your n+3 iteration with not only the one before n+2 that will be the fixed point, but you are also connecting to the previous one with with an expression that try to mimic the essentially the Newton method, but without the need of the derivatives. So they don't really, these methods, the vector acceleration methods that proposed quite some time ago, they don't really complicate your the model.
So you would
That's
use
nice.
it in any kind of cycle, even if it just two beds for steps.
Yeah, yeah.
Okay. Then we have a question from the audience on YouTube by Rodinson Rieta Perez. He's writing, "Hi, Professor Gazzani. Thank you for your interesting presentation. Have you simulated some process in which the adsorbed molecule have been desorbed by a reaction? If yes, how did you model this?"
Well, yeah, that is the case for sorption enhanced water gas shift. In the sorption enhanced water gas shift, you have a coexistence or reaction with adsorption, because that you want to basically push the shift, the water gas shift further to the products, because you are removing the product itself, the CO2, that you don't have the typical equilibrium limitation by reaction. So in that case, what you need to do is to, if you go back, yeah, maybe here is fine. So in the equations, you need to add in both the mass balance and the energy balance, you will need to add a source sink term that represents your reaction. So you will have an additional term that needs to account for the fact that some CO2 gets converted, for example, or for example, if you have if you are activating the CO2 that is absorbed with the hydrogen to produce methanol or methane, and in that case you will have that the sorbent removes CO2, but then there will be a consumption term that needs to account for the fact that CO2 gets also regenerated with the hydrogen, for example. So you need to adjust this equation to account for the reactions and the energy that it involves.
I think it's super clear. We have another question from Dr. Danacci. He says, "Are the original process Pareto fronts generated based on CSS results? If so, are there any potential issues with the constantly varying feed and potentially never achieving CSS?" Cycle steady state.
Yes, so let me go to this slide. So when you do this, you do this approach, the black box approach here on the left, the point that you evaluate, so the objective function that is returned to the optimization algorithm is always after CSS is achieved. So you simulate the cycle, you reach cyclic steady state, and what is found is passed to the optimization. So the optimizer will maybe identify that as a Pareto point, and if that is the case, it is based on a cyclic steady state condition. What might be challenging though is if you want to simulate, and that connects a bit to the system level that I was describing before, it's when you want to disconnect different points. So say that you have a Pareto front. Let me go to a Pareto front.
I think he was referring.
Sorry, Matteo, if I can interrupt. I think my question to Giuseppe was a bit unclear, so it's my fault there. I was referring to the year-long DAC modeling you were showing at the end of the presentation.
Okay, that's where I was going now. In fact,
right.
Yeah, that's yeah. Let me go there. Yes. So this is a very good question, in fact, because when you have actually, we can go to this. here, no? You have these maps, and then you have, let's say, select a point. This will give you an energy requirement for a given ambient temperature and relative humidity. Then this is for a certain instant of time. Then you have the next hour, and the next hour you need to identify where you want to operate. And what can happen is that your cycle to reach cyclic steady state requires more than an hour, which would be problematic, right? So what you need to do is to take care of that with constraints. So in our case, for example, in our work, we had a constraint in the MLP that said you can move to another point only if the cyclic steady state, the amount of time to reach a cyclic steady state in terms of moving from one condition to the other of the bed is within an hour. Otherwise, you need to be closer to the point, the original point. But this also opens up a bit the question of really pure control. That is, when you want to move from one operating point to the other, what do you allow to change? And that's what we did with this different operating configuration. So in operating configuration 1, we allowed to always be on the Pareto front. So we said, okay, we have a smart control that we didn't identify. So it will be something really nice for control engineers and academics to identify the control strategy that allow you to stay on the Pareto front. This configuration 2 instead was the case where we always had the operating condition fixed. So we were moving away from a reference operating condition at the Pareto, and then things were changing with the weather condition, and the resulting operating point will be on a different position. And in fact, that different type of control leads to a completely different operation in time. But indeed, good point. This has to be adequately taken care of, typically with constraints in the MLP.
Thank you.
You're welcome.
We don't have other questions on the YouTube channel, but I do still have a last one, if you don't mind. Slide 49.
I lost Giuseppe.
Slide 49. It was about the gradient-based, evolutionary, population-based, model-based, derivative-free approach.
Yeah.
So that's more a personal question. What is the one that you have used the most of the one, or do you have any preference here?
Yes, so you can, let me see, where is that reference? Yeah, so you can refer to this paper, Young and Bigler. They discuss many of these things. And also in the paper that we wrote, we discuss a few of these things. So I would suggest you to look into these two papers. And I must also say that that a priori, let's say, well, gradient base is really not working well for the type of problems that associated to adsorption. But in principle, one shouldn't be shouldn't decide a priori that one is better than the other. So one should look into what are the different possibilities. And I'm not a mathematician, so for us it was what do we think is the best algorithm that would fit well for adsorption, for cyclic based adsorption, and we identified the MCS. But I for example, there is this CEMO, the algorithm that you can also find on GitHub by Arthur Schweitman. It's professor at TU Delft. That works also very well. And also, I think that commercial solvers that are, for example, Baron, that is simply an optimization algorithm that or tool more than an algorithm that is designed for non-convex problems, nonlinear problems, so might work very well as well. So there are multiple options, and one shouldn't just stick to one or the other. Just see what works best for your application. Always try a few if possible, essentially.
Thank you. We have a last question from YouTube,
Yeah.
the YouTube channel, from Nicolas Antunes. He's saying, thanks, Professor Gazzani, for such a comprehensive presentation. At which point of the design cycle would you consider appropriate to swap the 1D model of the reactor to a detailed 2D, 3D description?
That's a good question. I think it depends a bit on the where you're doing this work. So I would say that in academia, typically is quite difficult to go from, but it would be nice. It would be difficult to include all these aspects and also a 2D, 3D. Maybe something for yeah. But however, so my point would be when you have an idea of how the technology, so the design of the contactor, so the contactor is selected, so the geometry, the material is selected, the application is known, and more or less the different operation modes are known. At that point, going to CFD based options, or your own code for 2D and 3D. But I think that the 2D, 3D is not really meant for this type of optimization. Maybe something interesting could be to use a CFD or a 2D, 3D approach to use it for a surrogate model with machine learning or similar. That might, if one has a good computing infrastructure, might run some few hundreds of simulations and then move ahead with optimization with a surrogate model based on the 2D, 3D. But yeah, I think that the contactor design, are we talking about a monolith? Are we talking about a packed bed? So these type of things need to be clear and not optional before doing 2D and 3D. A bit of a different approach, I think, would happen in industry, where they have more specialized teams, and that might be might happen in parallel in that case. But if as a single person that need to do these different things, I would I would suggest what I said before, essentially.
Thank you, Dr. Gazzani. We do not have any other question from the audience, so I think I can leave the floor for David.
Thank you.
Great. Thank you very much, Giuseppe, for your assistance today moderating the Q&A. And I'd also like to thank Dr. Matteo Gazzani again today for his presentation, assessing and optimizing adsorption processes from a plant and system perspective. We also thank all of our attendees for joining the webinar and hope you found it educational and/or enjoyable. And an edited version of the webinar will be posted on the IAS YouTube channel and also Bilibili. And we'll usually notify everyone on the IAS Twitter account when that occurs. Our next confirmed webinar will be given by Dr. Jenny Vittio from the University of Insubria on September the 18th at the same time, 1400 UTC. And any announcements of further webinars and other events will also be posted on our Twitter account and through the IAS mailing list. With that, we thank you for joining us, and we hope that you'll join us again soon.